Welcome to a short demonstration of WEST 2009. In this demo, we'll show you how to graphically set up the layout of a plant and how to prepare and run a dynamic simulation. We will not have time to start from scratch, so we'll use these templates that you can see in this overview pane. Is a conventional activated sludge unit and uses the ASM1 as the description of the biochemical processes. Now I click the open button to start up the project. There we are. And what I'm planning to do is to add a controller to control the aeration in the aerobic tank. So I open up the process unit library, look for the appropriate controller model, the PI controller, and drag it on the layout sheet like this. Next, I need to connect the terminals of the controller model to the terminals of the aerobic tank model by drawing a connection like this. Every time you establish a connection of this type, you have to indicate which variable is transferred across the link. In this case, the controller will get the DO measurement from within the tank, but you see here you have several options of measured variables. We'll pick the DO and link it to the input variable of the controller model. We'll do the same on the output side of the model and connect the output signal of the controller to the relevant model parameters, the KLA, which controls the aeration like this. Now, what we can do is have a look to some key model parameters. So if we select this process model, this process node, the controller, and activate the process detail, you will see here that the set point for, in this case, the DO concentration in the aerobic tank is 2 milligrams per liter, and the KLA will range between 0 and 100 days to the -1. If you now select the anoxic tank, the volume is 2000 cubic meter. The volume of the aerobic tank is 4000 cubic meter. The underflow of the clarifier is set to 18,000 cubic meters per day. Now, a crucial aspect of wastewater treatment plant modeling is the characterization of the influent. WEST 2009 has a tool termed Influent Generator, which assists in setting up the influent file. I will now double click on the input process unit, in this case the municipality, to access the wizard. In the practice, you will measure a number of quantities, typically COD, TSS, TKN, but you may have other quantities, and you can add them to this list. Ultimately, these quantities will need to be converted into the model variables through what is referred to as fractionation model. In WEST, you can set up such model graphically by dragging the appropriate blocks from this library and assigning the appropriate connection values to the connections. I will not go into the details of this procedure, but simply select a pre-existing fractionation layout, which applies to the ASM1 model instance that we selected at the beginning. There it is. And move to the next step. Here I'm asked to provide a data source to each variable of my influent characterization. So I simply browse and select an appropriate input file. Now, if the file is written in a certain way, the association is made automatically. Otherwise, you can always go and select the data series manually. Then I click Next. And this is the result of the application of the fractionation model to the set of measurements. On the left, you have the original data set with COD, TKN, TSS, and on the right, the resulting influent characterization expressed using the model variables. Now, we'll confirm all this, and the influent model will be generated in the background. There we are. Now, I want to show you one last thing before actually running the simulation that you will hopefully find very convenient and easy to handle in West. That is preparing the simulation output and specifically a plot output. I intentionally left this plot empty so I can show you how easy it is to create a plot that shows the quality of the effluent, like in this case. So what you will do, you simply select the appropriate process unit on the layout sheet, go to the variables tab of the process detail, select the relevant variables, you can multi-select, go back to the output sheet and drag the selection. And there it is. The plot is ready to receive the simulation output. Now everything is ready for the simulation, but first of all I will have to run a relatively long steady-state simulation that uses a steady-state influent so that the system can reach a steady-state condition. This will then be used as initial condition for the dynamic simulation. It should start in a couple of seconds. There it is. Now at the end state of the steady state simulation will be used to reinitialize the system and will enable us to run a meaningful dynamic simulation like this one now. So this is the output of a dynamic simulation in West. I hope you enjoyed the short. Thank you.